And yeah, next up we have our second presenter, Rami Maassarani from Loyalist Township in Ontario. So we'll move right along now with Rami's presentation. Rami is a professional engineer and a graduate of Queen's University, where he completed both a Bachelor and a Master of Applied Science in Civil Engineering. He has been with the engineering division of Loyalist Township since 2015 and has worked on a variety of projects ranging from water and wastewater infrastructure to climate action planning today. He will talk about his work on the Amherst View Water Pollution Control Plant in Loyalist Township next. So please join me in welcoming Rami, and Rami, the floor is now yours.
Thanks for the introduction, Yvonne, and good afternoon, everyone, and thank you for joining me today. So my name is Rami, and I work in the engineering division at Loyalist Township, a small municipality in Eastern Ontario, which is situated on the traditional Anishinaabe and Haudenosaunee territories. Today, I'm going to talk to you about a project which demonstrates that sometimes the solution to a problem can be found if we're willing to look around us and think outside the box. This project was a collaboration between Loyalist Township and Queen's University and was made possible thanks to funding from FCM and the Green Municipal Fund. So as a bit of background, the Amherst View Water Pollution Control Plant services the communities of Odessa and Amherst View. It treats water from the equivalent of about 4,000 households or about 10,000 people. The mechanical portion of the plant provides the bulk of the treatment, but we also have a series of polishing lagoons which provide passive disinfection to the treated waste stream. So treated wastewater from the plant is discharged into a natural wetland called the Bayview Bog, and we'll come back to this in a second. But here's a quick graphic of how water actually flows through the plant. So the main plant is at the top of your screen. Water goes down into Lagoon Cell 2, does a little loop round into Lagoon Cell 1, through Lagoon Cell 4, and then out of the plant. So what was the problem? Well, we found that during the summer months, we would typically observe elevations in the pH values of the plant's final treated stream. And it got to the point where sometimes the plant would actually be out of compliance with this license. We figured out that the increase in pH was actually caused by algae blooms in the disinfection pond. So we can kind of see that little circle there in cell 1, which really elevated the pH through a bunch of chemistry processes, which we're not going to get into now because they frankly escape me sometimes. So really the question though became, how can we treat the pH of the waste stream, or how can we attenuate it before discharging it into the receiving environment? So we looked at several options over several years, and typically a solution for a problem like this would have involved getting rid of the lagoons and replacing them with a conventional treatment system. So, chemical addition or UV disinfection. The problem here, though, is that these systems can be quite expensive, not only to build, but also to operate. So we just started looking at other options. And here's really where it gets quite interesting. Previous study of the Bayview Bog. So again, that's the natural wetland into which the waste stream of the Amherst View sewage plant is discharged. So the study demonstrated that the elevated pH of the plant's effluent would actually be rapidly attenuated in this wetland. The study spanned several years between 2006 and 2009, and it was undertaken by a team of researchers from the Civil Engineering Department at Queen's University, and it was actually quite closely followed by our local Ministry of the Environment, Conservation and Parks Office, as well as the local Conservation Authority. So with the results of this study in hand, a plan was put together to build a wetland within the confines of the Amherst View Water Pollution Control Plant. So this involved a lot of coordination with a lot of different groups and stakeholders, which included the Township, the MECP, the CRCA, so Conservation Authority, and the same team of researchers from Queen's. So what we elected to do is actually convert the final lagoon, so Lagoon Cell 4, into a constructed wetland, which would use the same natural processes found in the Bayview Bog to attenuate the pH of the wastewater before it's discharged from the plant. So pulling this off would actually result, or effectively result, in a cost-effective and sustainable solution to our problem. Now, the project team was made up of a few different groups, so Loyalist Township and our staff, as well as Queen's University. So the same researchers who conducted the Bayview Bog study was involved in the wetland project. The Ministry of the Environment, Conservation and Parks, as well as the local Conservation Authority, were supervising and following the project as it went along and providing some recommendations here and there. and also the contractor who went about and did the construction on the project. So we spent a few years designing a wetland that could fit within the confines of Lagoon South 4. And what we ended up with is what you see in the model here. So each cell would be planted with cattails. So this is one of the main plants that would be found in the Bayview Bog, so that we can replicate the natural process as closely as possible, right? So if we have plants in the natural wetland, we just want to take the same plants and put them inside of our system, just to be as accurate as possible in our replication of the system. So we also included 4 parallel trains so that we could compare the effectiveness of different growth media for the cattail. So one train was seeded with topsoil, another one with sludge, another one with peat, and then another one also with peat, but with a different flow characteristic. So we could just compare the different, or a few different changes and just see what worked best. So what we ended up with is something that looked like this. We finished construction and we brought the system online in 2016, and we went to open the valve and it didn't work. So we quickly began experiencing hydraulic flow issues, and that water would start pooling where it wasn't supposed to go, and then it wouldn't go where it was supposed to go, and we just couldn't control water levels inside individual cells. So we just had to take the whole thing offline and just go right back to the drawing board. So as I said, we identified a need to control water levels inside individual cells so that we could enable cattail growth, right? So if we were seeding these plants across the wetland, they needed a saturated media during their early growth stage, but the water level couldn't be too high. But as the plants grew, and if anyone's familiar with cattails, they do get up to 2 meters in height or even higher, the water needed to increase with it. So we needed to allow ourselves the option of actually controlling the water levels in individual cells, so that we could increase water depth as plants grew till we got to the operational depth. So we did what we should have done in the first place, is we actually talked to the people who would be operating the system, and we came up with a solution that would actually help, right? So the flow control structure you see on the right of your screen is what we came up with. So it was an idea that was thought up by someone in our utilities division, engineering designed it, and then our public works staff went and built it in-house. So it was a bit of an unconventional system, but really it worked quite nicely, and this is what we ended up with. So we brought the contractor back online, back on site in 2017, or late 2017, and let me tell you that construction work in late November, early December was a little bit chilly, but we got it done. And we installed these new structures in each cell. We also took the time to reinforce some berms and modify a few slopes, but really overall, the construction was staged in such a way as to not affect most of the wetland. So we were able to control water levels in individual cells, just like we'd hoped to, which helped create a favorable growth conditions for the plants. We went back online in the spring of 2018, and we started seeing some rapid cattail growth. So we started off here, this is about 30 centimeters high, going to 6 feet high or slightly more. And really what we ended up with is was this nice wetland where you can still see our 4 parallel trains, but really nice, thick, dense vegetation with plants that are well over 2 meters high. The added bonus here is that it works, yes, but it actually also acts as a carbon sink. So if we think back to what our original plan was of just putting in a conventional UV system, now we have the opposite, where instead of using energy, or producing greenhouse gas emissions, we have something that acts as a carbon sink, which is kind of neat. Just a quick summary of project timelines. Really, the main purpose of showing you this is to demonstrate how long the whole process took. All right, the design itself took a couple of years. Construction work took 1 year. Then we had to redesign, reconstruct, and implement the project. So really, we're looking at 5 years from start to finish. And this doesn't even include the initial Bayview Bog study, which ran for about 6 years in the early 2000s. So even though it might seem like an exercise of just moving dirt around and seeding some plants, it actually was quite the process that took a fair amount of time. And just because we can't make it through a whole presentation without at least one graph, and it's the only one I promise, here's a slide that shows that the system has been working, or how it's been working since we brought it online. So we have a few things going on here. The orange line is the pH of the water going into the wetland, and the green line is the pH of the water coming out of it. We also have two horizontal lines. The one on the top is the plant's effluent limit, so we really can't go over this line. And the lower blue line on the blue line, that's the second one from the top, is our objective, where we want to stay below this line, but if we go slightly higher, it's not the end of the world as long as we stay below the red line. So what we can see here is that the wetland is actually working as we were hoping it would. The pH of the water coming out of the system is always below the red line. But more interestingly is as the wetland actually matures a little bit and the plants grew and got a bit more settled in, we're actually consistently below our objective, which is great, even though the water coming into it is higher. So all this to say is that the system is working as it was supposed to, which, trust me, was a relief. And that as it grows, or as it gets a bit more established, we should see this trend continue where we'll consistently be below our effluent objective. So really there's a couple of takeaways from this project, but the main one really is that sometimes a solution to a problem can be found by just taking a look around us. Right, so the township could have elected to choose a more conventional approach to dealing with the elevated pH of the Amherst UWPCP's treatment stream, but instead it elected to let nature take care of nature. By working together with a diverse team of operators, researchers, conservation authorities, and ministries, we were able to come up with a unique solution to our problem. The end result was a treatment process that accomplished everything we needed it to, while doing so in a passive, net zero energy manner, which provides additional environmental, economical, and social benefits. So really that's it for me today. Thank you for your time, everybody, and I'd be happy to take any questions you might have about our project.